Good day, everyone. So, in today's lesson, we'll be looking at properties of waves. Waves exhibit fascinating behaviors as they interact with different media and with one another. So, in this lesson, we'll be able to consider five good properties that they exhibit when they interact with different media and with one another. So, let's dive into this property one after the other. The first property of a wave is called reflection. In wave, reflection occurs when a wave encounters a boundary and then it bounces back. And just imagine when you are playing table tennis and when you serve the ball, then the ball is being sent back by the opponent. That is what we call reflection, when something bounces back. The wave also does that. And this is a typical diagram of how reflection occurs. Now this line, this red line you see here represents the wave itself. Okay, why this is the barrier or the boundary where the wave is approaching. By the time the wave gets to the boundary, what he experiences is a reflection, so it goes back. The red line you're seeing represents the wave. In this case, we are making use of light ray as a wave now. So the ray, because the incident ray goes an incident on the barrier or the boundary, then the boundary sends it back and it goes this way. Now the vertical line that separates the the incoming wave, or which you call the incident ray, okay, is that line is called the normal. Okay. Now the wave, when it gets there, the point at which it bounces back, the normal line is being drawn. Now the angle between this normal line and the incident wave is called angle of incidence. Again, the wave is being reflected and it goes this way. We call it the reflected wave. Now the angle between the reflected wave and that same normal is called the angle of reflection. So it has been found that the angle of incidence, the angle here, let me make it visible. The angle here, this angle is called the angle of incidence. This angle is called the angle between the incident ray and the normal here. It's called the angle of incidence. It has been found that it's the same thing with the angle of reflection. So they are the same thing. That is, the I is the same thing as well, the R. So angle of incidence is the same thing as angle of reflection. All right, and this reflection property is applicable in transverse wave and longitudinal wave. So both transverse wave and longitudinal wave exhibit reflection property. All right. So having said that, maybe we proceed to the next one. Another property of a wave is called refraction. Now, there are times that the boundary might not reflect this ray. In the previous one, we could see that here there is a reflection that occurs here. The wave gets to the boundary and then is being reflected. But there are some boundary or media that allow the rays to enter through them. Okay, so in that case, we cannot talk about reflection property. That takes us to refraction property. When a wave is being incident, okay, in this case now, it's coming from a medium, it's coming from air medium. Now let's talk about light as a wave, light wave now. So this light wave is coming from the air, okay, so that from the sun, for example, the sunlight now coming from the air, and it now gets to a glass. You know, of course, when the light gets to a glass, it can pass through that glass. It's not going to be reflected by the glass. So it enters that glass. That glass is another medium on its own. Then as it enters, it changes the direction. Look at this diagram here now. This orange line represents the wave, the coming wave, which we call the incident wave now. When it gets here, you can see that the direction has changed. So the direction has changed, okay, due to the change in velocity of that wave. On a norm, if you look at it very well, what we should expect to see when the light coming from the air when it gets here, when it gets to this point of contact, it's supposed to maintain the same direction like that. But it's not so. It's supposed to maintain this direction like this, maintain it when it got to the other medium, which is, let's call it water now, or glass. But then it had to move towards this normal line. That is because there's a change in direction. And this phenomenon is called refraction. When refraction occurs when a wave enters a medium that has different propagation speed and then cause change in direction. So the direction is no longer this way, it has moved to this direction. Okay, this way, move here and then bend. So that change of direction in another media is what we call refraction. We say refraction has occurred. All right. So what happens is that sometimes even the refraction can be away from the normal. It can go this way. But when do we expect it to go away from the normal? And when do we expect it to go close to the normal? Like the diagram we see here now, this particular one is moving close to the normal. So what really happened? But now this is how you're gonna know. For a wave to move close to the normal during refraction, it depends on the medium that is entering. Okay, so when it is moving away from the when it is moving away from the normal, that means that the the density of the media is less. Okay, the density is less. But when it is moving close to it, that means the density of that media is high. Okay, so very important that you know why it is moving away from the normal or not. All right. The another thing is that if the speed of that medium is high, it moves towards it. But if the speed is low, it moves away from it. But the point here is that the change in direction, whether away from the normal or close to the normal, is due to what change in velocity of the wave in that medium. So I want said about talk on the second property. Let's talk about the next property of a wave. That's called diffraction. We have seen a scenario where it's being reflected by a boundary. We have seen a scenario where it's not reflected, rather it's allowed to enter into that medium. But in this case now, there is now another experience whereby there is a space. The boundary is now creating a space for the wave to pass. Look at this diagram here. Now there is a space for this wave. This line you are seeing here is wave. Now this is the boundary, so there is a space here for the wave to pass. When there is a space created by a boundary for the wave to pass, the wave will spread around that boundary. You see, when the wave was coming and it got to that boundary, it began to spread around it. Now look at this other one again. This space here is smaller than the one here. You can see that when we have a smaller space, that the bending around it is more than when the space is bigger. So the smaller the gap or the space, the more the diffraction. This phenomenon is called diffraction. Diffraction is the bending of waves around obstacles. Okay, so when they go to that obstacle, they begin to what? They begin to bend around due to the space. So this phenomenon is called diffraction of wave. Smaller the space, the more the diffraction. The lesser the space, the higher the space, the lesser the diffraction. Now, the fourth property of a wave is what we call the interference of wave. Now, interference happens when two or more waves meet in the same region of space. Okay, and they are of two types. We have the constructive interference and we have the destructive interference. Now, look at the example of constructive interference here. This is one wave. Okay, going the one up is one wave, the one down is another wave. They are both in the same space or the same region. Now, in every wave representation, we have what we call the trough and the crest. The crest is the peak part of the wave, like this now, the crest. Let me indicate that. This is the crest here. Now look at the crest. The first wave, let me call this wave 1, and this is wave 2, right? In the same region, they are in the same region, yeah. Now in wave 1, the crest is the top part. part, this peak. Okay, while the down part is called the crest. Okay, now it is constructive because the crest of wave 2 is the same line, is meeting with the crest of wave 1. Whenever this happen, what the result you will get is larger wave. You see, we get larger wave with larger amplitude. The amplitude will be higher and the wave will be bigger. Okay, so this type of interference is called constructive interference. When two waves meet in a way that the crest of one is in line with the crest of the other one, then you get constructive interference. But at the other hand, the destructive interference is when the crest of one is in line with the trough of another. The trough is the down part. In this case, now this is the crest here, while it is the trough. This is wave 1 and this is wave 2. So when the crest and the trough are the one in line, then the result is called destructive interference. You will get a smaller or zero amplitude. You see that there is no amplitude here at all, it's just a straight line. While this one has an amplitude. Amplitude is the maximum height, okay, of the wave. So for destructive interference, we get no or smaller amplitude, but why for constructive we get high amplitude and then a bigger wave form. So this is the fourth property of wave. It happens when two or more waves meet in the same region of space. All right. Then the fifth one is called polarization. Now, polarization simply refers to the alignment of oscillation of a transverse wave in a specific direction. You see, the last four properties we've mentioned can be found in transverse wave and in longitudinal wave. But this polarization is peculiar only to transverse wave. So the difference between transverse wave and longitudinal wave, that property is that the polarization is only found in transverse wave, while longitudinal does not exhibit this property. Okay, now before when we say polarization, we say it is the alignment of oscillation of a transverse wave in a specific direction. Look at this light now that is being turned on. The light ray begin to move in different direction. Okay, this is called unpolarized wave. When they enter specific direction, it goes to the north, it goes to you go to the north, you go to the east. Okay, but it still has a target where it's going to reach. Now that is called unpolarized wave. Now we now place it before a polarizer that now allow the wave to move just in one plane. Then the result you get is called a polarized wave, and it's only transverse wave that exhibits this characteristics of moving in different direction perpendicularly to each other. So when you now get a polarizer that makes it to move in one plane, then you get a result called polarized wave. So for this part now, the one on our left hand side is unpolarized because we see the yellow part of the light is at 90 degree to this direction of propagation, while the blue part is at also 90 degree to the direction of propagation. So they are perpendicular to each other, and that is how transverse wave behave. But now when they go through this polarizer, we have a polarized light. So that is moving in just one plane. So polarization is the alignment of the oscillation of a transverse wave in a specific direction as that one plane here. And this does not apply to longitudinal wave. Then there's what we call standing wave. Standing wave. Now, standing wave is possible when two waves of the same frequency and amplitude, very key, they must be the same frequency, they must be the same amplitude. So when two waves of the same frequency and amplitude travel in opposite direction and superimpose, or when we say superimpose, that means they cross each other. Okay, then we say that what standing wave have occurred. Okay, we call it standing wave or stationary wave because it not look as if nothing is happening. There is no movement, but it's up what movement is taking place. And when standing wave occur, two things will be noticed. We have node and we have antinode. This is a typical diagram of a standing wave. You see the unbroken curves is one wave, okay, while the broken line is the second wave. Second wave is coming in the opposite direction like this. So let's make it visible. Now, this first one, the thick line is approaching this, is going this direction. This is the direction of this particular one. It's going like this. All right, it's going this way. Now, the other one is going in the opposite direction, this way. We know that is what defines a standing wave. There must be two waves that are in the opposite direction and they must have the same frequency and amplitude. And when this occur, you have what we call node. This place is called node. This point. What is a node? A node is a point of minimum displacement. You see that that's the minimum displacement I'll call here. Why antinode is a point of maximum displacement. When the wave gets to the maximum point, they come down. Okay, so in a standing wave, we have node, in point of minimum displacement. We have antinode, a point of maximum displacement. So we can find this kind of experience of standing wave in string and most open-ended ended pipes. So string, well, the string we are talking about is musical instrument like a guitar. All right, so that's how superposition of progressive wave occur. When they superimpose, they form what we call the standing wave. So what have we learned today? We've been able to understand the wave properties, which are reflection, refraction, diffraction, interference, and polarization, and we're able to know what standing wave is all about. All of these properties are very essential in this subject. All right. Now, in reflection, we find out that the angle of incidence is the same thing with the angle of reflection. In refraction, we're able to see that it occurred due to change of speed of the wave. Okay. And in diffraction, we find out that the wave also bend around obstacle. Interference, we find out that we can have a constructive one that is a bigger wave, or we can have no wave at all when interference occurs. And in polarization, we're able to see that we can align a wave to move in one plane, okay, which is called a polarized one. And we say standing wave occur when two waves of the same frequency and amplitude move in the opposite direction and they form node and antinode. So having said this, maybe we should just take one or two questions and then we call it a day. Look at this question here. It said, which of the following properties is or are common to all waves? Okay, number one, we have diffraction. Two, we have refraction. Three, we have interference. So let us see. Option A, we have option A, we have only B. Option A, we have one rather. Option A, we have one. One is diffraction. No. Option A is not correct. In what is common to all waves are diffraction, refraction, interference. The one that is not common to all is polarization. Polarization is not listed there. So our answer should be the three of them. So A is just I, B is I only, C is I and I, D is I, D is I and I. So D is correct. It's only polarization that is peculiar to just transverse wave and it's not listed there. So D is the correct answer. Next question says, which of the following characteristics of a wave is used in the measurement of the depth of the sea? For you to measure the depth of the sea, there must be reflection. Okay, and it is reflection that is being used as property here. Okay, it's with reflection that we use, making use of a machine called sonar. So now we have, through reflection, we're able to know the depth of the sea. All right. The next one says, which of the following is the exclusive property of transverse wave? We already know that is what polarization. It's only polarization. It's only transverse that is a bit polarization. No other wave exhibit that. All right. Now look at this question here. So the diagram below shows two waveforms P and Q at a particular instant of time. Okay, this is wave P and this wave Q. So the two waves will interfere A destructively to produce a wave of a larger amplitude. Look at it here now. You could see the crest of Q is the same in line with the crest of P. So this is a constructive interference. So you're going to, and if it is constructive, you will definitely get a larger wave. So A says destructive, no, it's not destructive. B also says destructive, no. C say constructively to produce a wave of a larger amplitude, yes. C is correct. D say constructively to produce a wave of a smaller amplitude, no. When it is constructive interference, definitely the wave you will produce will have a larger amplitude. So D is contradicting itself. So C is the correct one. It is constructive because the crest of Q is in the same line with the crest of P, and they will give us uh, a larger amplitude. All right. So let us take one more question. He said, transverse wave can be distinguished from longitudinal wave using the classes of what? Of polarization. The other properties are exhibited by both longitudinal and transverse. But for polarization, polarization is the only property that is exhibited by transverse wave alone. All right. So the next one says the phenomenon of light bending around an obstacle is what? Reflection? No. Reflection is bouncing back. Polarization? No. This one is aligning in a single plane. C. Refraction. Refraction? No. This one is entering another medium and changing direction. D. Diffraction? Yes. Diffraction is the property that allow light wave to bend around an obstacle. All right. So we say diffraction of course. All right. So I'll be doing the cutting here today. I hope you'll be able to learn all the properties of wave and the example that involve. Thank you for listening and have a wonderful day for now. Bye.